So hello everyone and welcome to this week's video lecture. So in the previous lecture, I had started with the SEPIC converter and we had created the circuit schematic, which is this one, and we had actually imported the CHUK converter parameters and we had renamed it as the SEPIC converter parameters.csv. So this really is the CHUK converter parameters. So just to get accelerated, I had imported the CHUK converter parameters, renamed it as SEPIC converter parameters, and in this lecture we'll continue ahead with this. So as before starting this lecture, a little bit of background that in case you are interested in these kind of video lectures on power electronics and electrical engineering in general, I do have a complete online course on this topic. That is, I have an online course called Simulating Power Electronic Circuits using Python on the MOOC website Udemy, and in this I go through an entire overview of the entire process of using Python for simulating power electronic circuits. So this includes installing the software, simulating several types of circuits, a little bit of basic theory about power electronics, and finally there is an entire case study of simulating a buck converter, which also includes closed loop control. And if you are interested more on the control digital signal processing side, I have another course called Basics of Digital Signal Processing for Power Engineers, and in this I use Python for designing filters specifically for power engineering purposes. So once more, in this there is a basic theory of signal processing, there is a little bit of tutorial on Python, and eventually we simulate several filters. So basically we simulate analog filters digitally, we simulate specific digital filters, we go through the implementation, and we also simulate. So these two courses are there in case you're looking for video lectures but you want something a little more comprehensive than these video lectures on YouTube. So with this background, I'll get back to the lecture. So to continue, as I said, we have imported the parameters of the CHUK converter into the SEPIC converter, right? So what we need to do is we need to now change some of those parameters to make it in tune with the SEPIC converter. So let's just go through all of them quickly. So first is we have the ammeter, which is C1 at one end. So let's go look for that. So this is ammeter C1 at one end and the direction is 1 0. So let's go have a look. The direction is 1 0 towards the right. Alright. Now, in this case, alright, in the case of a SEPIC converter, or rather in the case of a CHUK converter, we saw that there is usually a bidirectional flow of energy through the capacitor. So for example, when the switch is turned on, the current flows from the source through the switch in the clockwise direction, and the current from the capacitor discharges through the switch in the anti-clockwise direction. And when the switch is turned off, the SEPIC and the CHUK converter, in both cases, the inductor and the voltage source will charge the capacitor, right? So the same occurs even for the SEPIC converter, the same for the CHUK converter. So this direction of the current is perfectly okay because the current will flow in both directions through the capacitor, right? In both the CHUK converter and the SEPIC converter. So this is perfectly okay. We can leave it as it is. Then comes the ammeter Cout. Let's go there and have a look. Ammeter Cout. So this is the ammeter Cout here, right? This is the current through the output filter, or rather output capacitor branch. So let's go have a look at what's going on. So this is 11 AA and the positive direction is 10 AA. Now here there's a difference. In the CHUK converter, the polarity of the output is reversed, right? So which means if the input has a polarity with a positive polarity towards the upper terminal, the output voltage will have a positive polarity towards the lower terminal, right? So which means the current in this capacitor, in the case of a CHUK converter, is flowing upwards, and that's why the direction of polarity of the ammeter is upwards. In the SEPIC converter, that's not the case. The output voltage has the same polarity as that of the input voltage. So now the current through this capacitor flows downwards. So this will not do. We cannot have the polarity upwards in the case of the ammeter. So let's go change that. So I'm going to make this 12 AA. That is, it is downwards. So we're done with this. Next comes the ammeter D1. So let's go have a look at where D1 is. This is ammeter D1 and or rather this is D1 And let's go have a look at where this is. The positive polarity direction of current is 12S. Now, here again, there is a difference. In the case of the Chook converter, it was the inductor which is actually on this branch. The diode is in this branch. Here in this case, the diode is in the forward branch and the current flows towards the right. Alright. So, therefore, having this current point in this direction doesn't make much sense. Right? You have to point in the right. So, what we need is to make it 1x. And then comes L1. So let's go have a look at where L1 is. L1 is here. This can remain as it is because I don't think it changes. Yes, it is. It's the positive direction is 1D, which means to the right, and that's perfectly okay. Then comes L2, which is its 7S. So let's go have a look at L2. This is inductor L2. Now the inductor L2 is charged by the capacitor, right? When the switch is turned on, the inductor is charged by the capacitor in the anti-clockwise direction or counterclockwise direction, which means the current flows in the upward direction, which means this current ammeter has to have a polarity towards the upward direction. So which means if this is 7S, this has to be 6S. So this will need to change. So save the parameter. And let's keep going. Ammeter In should not be a problem. It's 1A because this is the input side which is not changed. It should be 1B. It is 1B, so it's good enough. Ammeter load. Ammeter load will also change because a Chook converter, the output polarity is reversed. SEPIC converter polarity is the same as the input polarity, which means the upper terminal is positive voltage and the current will flow in the downward direction. So ammeter load will have to be downwards. So this will have to be, this is 6 AC, which is what it is. So it can be the same. The capacitor C1 is here. There is nothing much to do. The positive polarity is just for the sake of debugging. We don't really care. The capacitor value here we've chosen to be 100 microfarad. In the case of a SEPIC converter, we will see that the value of the capacitor can be lower because remember, the capacitor in the case of a SEPIC converter is not totally decoupling. In the case of a Chook converter, the input and the output are completely decoupled. All coupling happens through the capacitor C1, which means C1 needs to be large. In this case, in the case of a SEPIC converter, the input and the output are coupled. Therefore, this capacitor C1 doesn't have to be as large as before. But anyway, that we can look at more in simulation. So capacitor Cout can also be the same. It's 500 microfarad because the output bus is not changing. Then comes the diode. Diode will change, right? Now, where is the diode? 1U. Let's go have a look. So the diode is 1U, and we have already said that in the case of a SEPIC converter, the forward path is conducting. So basically, when the switch is turned off, the input voltage and the inductor, the energy, charges the capacitor and goes all the way to the output capacitor. Alright, that's what happens. And at the same time, the current in the inductor also discharges to the output capacitor. And both of this happen through the diode, which means the diode must conduct. And that can only happen if the polarity of the cathode is towards the right. So if this is 1U, the polarity of the cathode can be 1V. So this will need to change, and yes, it needs to change. So we need to change the rating to something larger, and let's make this 1S. Actually, we don't need to change the rating. I think the other ratings would also be 120 volts. Yes, because we are only dealing with a Chook converter, so we don't have to go to 1000 volts. Oh no, that was still not. I had to change it to 1V. I'll just change it again. So let me come all the way down. Here's diode, and I need to change the polarity to 1V. This is 1U, 1V is to the right. And we keep going. So this is the diode, then comes the inductor L1. Inductor L1 also does not have to change. We are using a 1 millihenry inductor, that's good enough. Inductor L2 is also 1 millihenry, we don't have to change it. We could technically change it because since if we are designing a practical SEPIC converter, but we are not going that far. Mainly we are looking at the operation of these converters. Then comes the resistor C1, which is basically a parasitic resistor. This can be 20 milliohm as before. Same goes for the resistor of Cout, which is the parasitic resistance of the output capacitor. This is also a very small value of 20 milliohm, can remain the same. Again, the resistor L2 is basically the parasitic resistor of the inductor L2, can remain small at 0.05 amperes. Resistor R1, this is the parasitic resistor of the source, and this is chosen as 0.1 ohms, which is perfectly okay, can remain the same. The load resistor is 10 ohms, can also remain the same, we don't have to change it. The switch F S1 is very important. So let's go have a look at what's going on. This is at 8F. So position is at 8F, and we know that when the switch is turned on, it has to conduct a current in the clockwise direction. That means the current through the switch flows downwards, and that can only happen if the negative terminal of the switch has a polarity downwards with respect to the component. So let's go have a look. This is at 8F, the direction of cathode is 9F. That's perfectly okay. So this can stay as it is. The voltage source can also be the same because it's just simple 12 volt battery that we are looking at, and the positive polarity is upwards with respect to the component. The component is at 8A, the positive polarity is 7A. Last is the voltmeter, which is C1. This is a voltmeter across the decoupling capacitor. This does not have to change. We've taken a positive polarity towards the left, right? So this is LK and this is 5. So basically 5L and 5K, which is towards the left. That's perfectly okay. Voltmeter. The voltmeter is basically pointing upwards, the positive direction, so we don't have to change it. So with this, the circuit is done. Alright. So before we forget, let us just export the parameters so that we have at least written the correct parameters to the params.csv file. Because if you remember from the previous lecture, we had merely copied the Chook converter parameters from the Chook converter simulation. So let's at least back this up before we forget. So with this, we can now keep going. Let's go back to the circuit list. Let's go back to the main page. And of course, once we're done with the parameters, we need to edit the control. So first and foremost, we need a control file. So let's go to the file browser. Let's go to the Chook converter. And as before, we need the gate signal.py and the gate signal _dsc.csv files. So let's copy these two, come over to the SEPIC converter and paste them. Right. So these two are the PWM generation for the converter, and they are common. We've been using it all the way from the buck converter, so nothing new. So let's keep going. So let's choose this file. Energy series, simulations, SEPIC converter, gate signal.py. So here let's PWM, write whatever you want, configure the control, choose the file, choose gate signal _desc.csv. Make sure you're in the right directory. So with this, we have now chosen the parameters or the control variables for this file. That's what the descriptor file does. We just upload it, and now we get all the control parameters. So very convenient. So now that we have this, we can just go over to our editor and check out this gate signal.py. So as before, the only change that we usually have to make is there is usually the setting of the modulation signal, right? Now, towards the end of every simulation, I create an open loop control file where I modify the duty cycle from 0 to some value like 0.8, right? Gradually. And then I set this changing duty cycle to the modulation signal where I apply PWM. So all I have to do is remove this because I don't have this file yet and assign it instead to 0.3 constant, right? So with this, we are pretty much done with the simulation. There is nothing much to do because the rest are all the same. We are not doing anything new. So we can just go back to the main page and go to the final view output file and let us run this simulation. So simulation is running, but as always, particularly when you have a control file, do not assume that it is running. Always go to the command line and check if that is indeed the case. And yes, we don't see any errors. We do see only success messages. These are success messages, right? So we're good to go. So let's just, for the sake of finding out what's happening, let's plot one file. So let's call this output voltage. Voltage plot, start the plot. Call this voltmeter VO, which is the output voltage. Call it VO. Save the waveform. Click on done and plot it. So let's go to file browser. We should see something. Yes, we do. And this is the result. Alright. So at least our converter is working successfully. Now, since this lecture is already getting a bit long, I will stop here, and in the next lecture, next week, we will go into a deep analysis of the working of this converter. So, as before, if you have any doubt about what I did, feel free to either comment on this video or send me an email or message me on social media, whichever is your preference. Otherwise, I will see you in the next week where we will continue with this and do a deep analysis of the waveforms of this converter. So, thank you so much for listening. Goodbye for now. See you next week.